Okay, so good evening. We will start today's session. So today is the extra session for this course. So I will cover the complete course overview in this lecture. So we start. So starting with the introduction of the aluminum alloys. The aluminum alloy has the density of 2.7 gram per centimeter cube, which is very less in metals. And because of this low density, it is very useful in the aircraft parts where we require the high strength, high specific strength. And the melting point is 659 degrees Celsius. Its boiling point is 2270 degrees Celsius. Thermal conductivity is 237. Thermal expansion coefficient is 23.5 into 10 to the power minus 6. Its electrical resistivity is 2.65 into minus 6 ohm centimeter, which is very less. Electrical resistivity is very less. So conductivity of aluminum alloy will be very high. So because of this higher conductivity, it's also used in electrical circuits or transmission lines. Its crystal structure is FCC, which possesses the highest strength and ductility. The lattice parameter is 4.05 angstrom. Atomic number is 13 and atomic weight is 26.98, which is approximately 27. And the it is paramagnetic material, means it's non-magnetic. It has very high corrosion resistance because it forms very thin layer of alumina Al2O3 on the aluminum surface around in few nanometers. So that layer is very adherent to the surface, so that prevents the further corrosion of the aluminum. Then its elastic modulus is 72, shear modulus is 27, and Poisson's ratio is 0.34. The impurities in aluminum means if we want to extract aluminum from the ores, So the general aluminum alloys have these general pure aluminum can have uh, impurities coming from its refining and extraction process. So the extraction process, sources of impurities, that is the first is the extraction process from the chemicals which refine used to refine the aluminum from its ore, anode carbon, and refractory lining and steel tooling. So from the extraction process, the alumina, iron, silicon, nitrogen, and gallium phosphorus are the possible impurities which can enter in the pure aluminium. The makeup chemicals can introduce phosphorus and silicon in the aluminium. From the anode carbon, the nickel, manganese, and iron is mixed with the aluminium. And from refractory linings to the tooling also, we will get the different some metallic or non-metallic impurities in the aluminium. So there are three types of impurities in aluminium. So first is the element in the elemental form. Second is the as the inclusions. Inclusions are the compound of metallic and non-metallic elements. So generally the oxides, nitrides, carbides, and borides present in the aluminium. Then gases as hydrogen. Hydrogen gas has a very high affinity in liquid aluminium. Liquid aluminium, and this is so high affinity in liquid aluminium. So too much hydrogen gas will dissolve in aluminium, and as the aluminium solidify, the solubility starts to decrease from higher to lower. So because of the decreased solubility, uh, that gas will try to escape from the liquid aluminium, but if the solidification rate is very high, so that will entrap the hydrogen gas in the solidified component. So that will result in the porosity of the in the component. So the applications of pure aluminum are in the electrical conductors. So the aluminum grade using an electrical conductor is the EC grade of aluminum, which has the 99.5% purity, and its code is 1350. Then in the packaging industry means it can provide the heat insulation. So packaging industry can be it is used in chemical industries, in household and architecture. Uh, it is also the aluminum or pure aluminum and aluminum logs are both you can be used in household and architecture because the uh, parts of this aluminum have good surface finish. Next is so the extraction of aluminium. In this the aluminium is extracted from its major ore, which is bauxite. So bauxite is contains the two types of minerals. First is the gibbsite and second is the diaspore. So gibbsite has the this chemical formula Al2O3 with 3H2O, and diaspore has the this formula. And in ore also, there will be some type of impurities, which are iron oxide, titanium oxide, and silicon oxide. So if we want to extract the aluminium from this ore, so there are two methods. First is the carbothermic reduction, and second is the electrolytic reduction. So in the carbothermic reduction, very high temperature around 2000 degrees Celsius are required to maintain very high temperature is required to disintegrate the alumina in the carbothermic reduction. So that is not a very useful process and requires very high amount of it's a very expensive process. So that's why we use electrolytic reduction, in which we use different types of salts which dissociates alumina into aluminium, and it is generally done at 220 degrees Celsius. So very less temperature, the extraction process can be done. Then further the electrolytic reduction has two processes. First is the Bayes process and second is Hall-Héroult process. So we will go through these processes one by one. So this is the Bayes process, where first the crushing, grinding and classification is done for the ore to reduce the size of the ore particle, and then those powdered foam ore is fed into leaching system, in which steam is provided. Then that in that leaching, settling of that suspension by mixing starch is done. So that suspension will then go through washing, then filtration. From the filtration, liquor and red mud cakes are obtained. So that liquor is fed into heat exchanger to cool the liquor. Then that liquor is precipitated. Then after precipitation, it is fed into the thickening section, where Al2O3 hydrate forms from the alumina. Then the rotary cleans from the alumina ore. Then that alumina hydrate is fed into rotary kiln to achieve the Al2O3. So the Al2O3 made from the waste process is further fed into the whole Herald process to achieve the pure aluminium. So in the whole Herald process, the cryolite is the main salt, uh, which is uh, used in dissociation of the alumina into aluminium. So after this process, hollow out process is used to extract the aluminium from the ore. Next is the refining methods. Means after achieving the aluminium metal from the electrolytic reduction, further refining is done to remove the impurities. So fluxing is done to remove the solid oxide. Means if there any compound, so flux are used to remove the impurities. So that remove the compounds and elemental impurities. Then degassing is done, hydrogen gas removal by vacuum. In the so by if so in vacuum the hydrogen gas escapes from the liquid aluminium. Then argon gas purging also used to remove the gas, and that some solid C2Cl6 tablets are also uh, fed into the liquid aluminium, so that these tablets react with the hydrogen gas and helps in releasing that hydrogen gas from the liquid aluminium. Then filtration is done to remove inclusions or any solid impurities. So there are four types of aluminum grades which are obtained from this uh, extraction and refining process. So first is the high purity aluminum, which has the 99.8 to 99.9 99.49% aluminum. Super purity aluminum have the aluminum concentration from 99.95 to 99.9959%. The extreme purity aluminum has 99.996 to 99.999% aluminum, and the ultra purity aluminum has greater than 99.999% aluminum in it. So this is high ultra high purity iron is used in electrical application. Then further we will discuss about the different types of aluminum alloys. Yeah, so this is the pure aluminum case, and if we add different types of alloying element in the aluminum, so that will result in eight types of aluminum alloys. So depending on the elemental uh, alloying element, uh, different series are formed. So the 1X series is referred to the pure aluminum, and if we add the copper, so that will result into the 2 triple X series of the aluminum copper alloy. So their properties are also shown in the uh, below box. So the pure aluminum is strain hardenable, exceptional formability, corrosion resistance, and high electrical conductivity. And if we see the properties of aluminum copper, so it have heat. It can be heat treatable. Means if we provide some heat treatment for this alloy, so precipitation will form, and that will increase the strength of this alloy. So it has very high. It has high strength, low corrosion resistance, and it is used in aerospace manufacturing primarily. Second is the 3000 series alloy, in which the major alloy element is the manganese. So aluminum manganese alloys have the highly formable corrosion, means highly formable, means the ductility is very high. It have these aluminum manganese alloys are good corrosion resistant, have medium strength. They are strain hardenable, means providing some deformation, the strength is increased. Then uses of this alloy is in beverage cans and tubing. Then if we add silicon, so that will result into the 4000 or 4X series alloy. So it is the aluminum silicon alloys are some of heat treatable and some are not heat treatable. Uh, They have very good flowability. So the good flowability and weldability is provided by the silicon present in the alloy. Silicon improves the fluidity of the aluminum alloy, so that's why its weldability and flowability is very good. Then it is medium strength alloy and used in automotive and filler materials in welding. Then if we add magnesium as a major alloying element, so that will form the 5 triple X series alloy. So these alloys are strain hardenable, have excellent corrosion resistance, high toughness, good weldability, moderate strength, and used in building and construction, automotive, cryogenic, and marine applications. And if we add the magnesium and silicon both as a major alloying element, so that will result in different type of precipitates in that alloy. So because of these precipitates, it have different uh, properties. So it is heat treatable, have high corrosion resistance. It have moderate strength, readily welded by gas metal arc welding and gas tungsten arc welding. These alloys have outstanding extrudability and plates for auto, automotive. Then if zinc is a major alloying element, so the zinc will provide the maximum increase in strength by forming the precipitates. from zinc and aluminum. So these alloys are heat treatable, have very high strength, special toughness versions, and used in aerospace and automotive applications. So if we further if we add the lithium, so that will uh, provide. So with addition of lithium, the density can be reduced of the aluminum alloy very drastically. So because of very low density and very high strength, these alloys are preferred in aerospace application. So they are heat treatable, have high conductivity, high strength, hardness, and generally the aerospace applications are used. It is used. So this is the aluminum uses chart means in different sector what is the percentage of the aluminum used. So generally it is used in transportation because of its low density and high specific strength. Next is so after adding the these different alloying elements in the aluminum, so what properties are enhanced and what are the mechanism which results in the higher strength of these alloys. So we will discuss those strengthening mechanism in aluminum alloys. So first is the solid solution strengthening. In that, five types of interaction results in the strengthening of the aluminum alloy. So first is the elastic interaction. Elastic interaction means the uh, if some alloying element size is less, means it's large or small, so the strain field created near it means it will impose some type of strain, tensile, or compression around its neighbor aluminum atoms. So that will result in the elastic interaction between aluminum and major alloying elements. So that will result in increase in strength of the aluminum alloy. Modulus interaction means both the alloying element and aluminum atoms have different modulus, so that will result into the strengthening. So the modulus will increase loc localized increase in modulus. Further, the stacking fault interaction can result in if the uh, some alloying element is present and that goes to the stacking fault. So uh, after going there, it will hinder the stacking fault uh, motion, and the stacking fault cannot rejoin after this alloying element addition. So because of that, stacking fault energy goes high, and that will increase the strength of the aluminum alloy. And electrical interaction means the valency of the alloying element is different. So valency is difference creates some dipoles in the in localized region where alloying elements are present in aluminum matrix. So that will, uh, because of that interaction, the strength increases. And the last is the dislocation interaction means yield point phenomena. Means if some dislocations are present in the material, so that dislocation also interact to each other and result in the more dislocation generation. So that will increase the strength. Second is the dynamic strain aging. Dynamic strain aging means means the stress or load bearing capacity depends on strain rate and temperature. Means if some alloying element is present, and so that alloying element will hinder the dislocation motion, and so dislocation motion hindrance can only occur if the alloying element have time to diffuse to the dislocation. So at low strain rate, the alloying elements can easily catch the dislocation and hinder their motion, but at high strain rates, they cannot uh, hinder the dislocation motion. And generally, if we see that with increasing strain rate, the strength of the load bearing capacity of that material increases with increasing strain rate. But in aluminum alloy, the with increasing strain rate, the alloying elements cannot catch the dislocation, and hindrance is less at high strain rate. So the load bearing will be decreased. So there will be less increase in strength, means the stress required at higher strain rate will be low. So that will decrease the uh, stress strain behavior of the uh, material at higher strain rate. And if so that means the with increasing strain rate, the stress is decreasing. So this is called the negative strain rate sensitivity. So this negative strain rate sensitivity result is called in the as the dynamic strain aging, and the temperature also effect is if temperature is high, so the diffusion will increases, and as diffusion increases, then the alloying element will catch this location easily and hinder the motion. Third type of strengthening is the precipitation or age hardening, in which means if we heat treat some aluminum alloy, so from the heat treatment, some type of precipitates form in the material, and those precipitate will hinder the dislocation motion by five methods. So because of that, the strengthening means the dislocation hindrance occur, and that dislocation hindrance will result into the hardening, so that improve the strength of the material aluminum alloy. So first is the stacking fault energy, means if stacking fault energy of a precipitate is higher, so the strengthening will be high, and if the stacking fault energy is less, so the strength precipitation hardening will be less. Then order structure hardening means if some ordering structure is present in the precipitate, so that order structure, if during the deformation, that will create some type of antiphase boundary. No, in antiphase boundary. So that order structure will contribute to the increase in strength of the material. The next is the modulus effect, means if the precipitate has different modulus, so the strain field near that will be different, and that will increase the strength of the material. Next is the interfacial energy, is antiphase boundary owns some interfacial energy near that region, so that will locally increase the strength at that point. So overall the strength will be higher due to antiphase boundary. Then the lattice friction means the precipitate uh, precipitate lattice friction with the aluminum matrix will result into the hardening. Then fourth point is the strain hardening. In strain hardening, if we provide some deformation, some percentage of deformation, so that deformation will increase the increase the dislocation density. And due to the increase in dislocation density, the material strength goes high. So how Means after strain hardening, if we want to improve the microstructure of that aluminum alloy after strain hardening, so then that aluminum part is is fed into the annealing process. So what is the annealing process? It has three steps: recovery, recrystallization, and grain growth. So in recovery, only slight uh, reorientation of dislocation happens, so that reorientation of dislocation restore the uh, ductility of that material to some extent. So in recovery, annihilation of point defects is occur, then formation of low angle grain boundaries. Uh, so by the orientation of dislocation in some arrangement, so that will create the low angle grain boundary. Then polygonization means dislocation are arranged in some manner like this. So this is called the polygonization. Then increment in so the this rearrangement of dislocation and point defects increases the electrical conductivity of the material during the recovery stage. Next is the recrystallization. So in recrystallization, nucleation and growth of strain-free grains happen. So means that the orientation level is higher in recrystallization because the temperature and deformation is also higher to occur the recrystallization. So that will create the small strain-free grains in the material. Means if the deformation is higher, then more strain-free grains will generate that will result into the finer grain size. Next is the grain growth. So these strain-free grains have different types of phases. Means some can be three, some can be four, five, and six, and more than that. So if this type of grains is present, so the grains which have phases less than six will shrink, and the grains which have phases greater than six that will grow. So the growth of some specific grains at the expense of small grains occurs. So in the grain growth, sometimes abnormal grain growth can also occur. Means some grain has extremely grow at the expense of other grains. So the that way is called as the abnormal grain growth. Next is the so this is the static recrystallization process. Means in annealing, it is static recrystallization. But the recrystallization can also happen during deformation process only. So during deformation process, recrystallization that is occurring is known as the dynamic recrystallization. So it is the recrystallization occurring during deformation is known as dynamic recrystallization. So when heat and stress is applied simultaneously during hot deformation process, it means that process called as the thermomechanical process. So that will thermomechanical process. So that will means the recrystallize the material during the deformation only. And one more thing is that means during the deformation, that plastic deformation also store strain energy in the material. So that strain energy means the plastic deformation, if it's tries to recover, so that will in means some energy is released, so that will increase the temperature of the material. So that increase in temperature also uh, provide the driving force for the recrystallization during the dynamic recrystallization. So the example for this can be hot rolling. So further, the dynamic recrystallization is divided into three parts. First is the discontinuous dynamic recrystallization. Second is continuous dynamic recrystallization, and third is the geometric dynamic recrystallization. So in all these processes, the different mechanism occur. So for discontinuous dynamic recrystallization, it generally happens in materials which have low stacking fault energy, and the continuous dynamic recrystallization occur for high stacking fault energy materials. And the geometric dynamic exercisation in this geometry of the grains uh, changes. So this that's why it's called the it means geometry of the grains uh, due to the rotation or movement of the high angle grain boundary that will result in geometric dynamic recrystallization. The next is the grain refinement method. So means after the annealing, except beside the annealing or dynamic crystallization, some more grain refinement methods are there to improve the strength of aluminum alloys. So first is during the melting and casting. So solidification behavior of the material is modified in a manner that leads to finer grain size. So nucleation is of two types. Is classified into two uh, types. First is the homogeneous nucleation, and second is the heterogeneous nucleation. So homogeneous nucleation is occur without any add of surface throughout the solidifying liquid metal, and heterogeneous nucleation occurs on the surface as defects, mold walls, second phase particles. So this heterogeneous nucleation is much more easier than the homogeneous nucleation. So if these defects are present in the material, so that will improve the nucleation rate, and because of the nucleation rate increasing, the grain size will be smaller. Means because the more grains are will form. So heterogeneous nucleation is more prevalent in practical scenarios because all time some type of defects will present in the during the solidification process. Next method is the melt inoculation. Means during the liquid aluminum solidification, some type of grain refining elements are added uh, into the liquid aluminum. So the major grain refinement elements are the titanium, boron, zirconium, tantalum, tungsten, vanadium, and niobium. So the grain refinement mechanism in melt inoculation are carbide and boride theory, in which the titanium carbide and titanium borides helps in the provide the heterogeneous nucleation site. Heterogeneous nucleation. So because of this heterogeneous nucleation provided by the titanium carbide, aluminum, or it can be aluminum boride also. So that will increases the strength, means that provide the heterogeneous nucleation during solidification and increases the uh, strength by refining grains. Next is the peritectic theory. Means peritectic theory is it is if some titanium is present in aluminum, so the titanium uh, this or Al3Ti particles is present in the liquid aluminum, so that will shift the solidus line to higher temperature. So at higher temperature, the alpha aluminum will starts to form is at a higher temperature. So that alpha, because of that higher temperature, the means the grain nucleation starts at high temperature, so that will result into the higher grain size. Similarly, peritectic Earth theory also says like it is the combination of Al3Ti particles and TiD2 particles. So both will rearrange in some manner that provide the heterogeneous nucleation site during solidification. Then hypernucleation is there, means some type of different type of uh, the elements are added, and so that will increase the nucleation rate. Then fading and poisoning. Fading and poisoning means the if zirconium and silicon is present in the material, so the zirconium and silicon hampers the solidification behavior. Means these zirconium silicon particles goes to the this L3Ti sites and block the complete ordering of the aluminium, alpha aluminium. So by avoiding the sequential growth of the alpha aluminium, these some type of microstructure changes occur because of this zirconium silicon. So that is called so the nucleation is decreasing in case of if zirconium and silicon is only present. So that is called as the fading and poisoning. Then the solute theory means this titanium and uh, carbide, titanium boroid helps in the heterogeneous nucleation in the aluminum alloy. Then next is the particle settling theory, means if we draw a grain size versus time. So at some time means the grain size is decreasing with the solidification time, and at some point it will starts to increase again because the particles means so means the nuclei which are forming in the liquid, so that will settle down at the bottom. So because of the settling of the nuclei at the bottom, the available nucleation sites will decrease, so that will increases the grain size for some time. And if we do stirring, so that will further decrease the grain size with time. Then next is the so third method of green refinement is the mechanical or electromagnetic stirring. So due to mechanical or electromagnetic stirring, more nucleation sites will be present in the liquid aluminum for the more nucleation of small grains. So there are four mechanisms which contribute in refining the grains during mechanical or electromagnetic stirring. So first is the shear mechanism of dendritic arm. So during the stirring, the dendritic arms will break uh, by the shear mechanism, and those broken dendritic arms is provide the heterogeneous nucleation sites. Then grain boundary infiltration. So at the grain boundary and the dendritic or solidified aluminum, some uh, energy shift occur, means the solid surface energy and solid liquid surface energy uh, changes at that point that will result into uh, more nucleation nuclei generation. Then remelting of dendritic root. So if the dendritic arm uh, have some means some condition of temperature on solidification rate, the dendritic arms can detach from the primary dendritic arm because of the melting of the dendritic arm root. So that will result in so that further those broken dendritic arms will provide the heterogeneous nucleation site. The crystal ring is called as the means the at the mold wall the small nuclei are formed in higher density. So if we stir this liquid melt, so these small nuclei will mix into the uh, liquid liquid aluminum alloy. So these by mixing these solid nuclei will disperse into the liquid aluminum and will further provide the more nucleation sites for the grains to grow. Then fourth method is the ultrasonic cavitation, means some pressure is provided. So because of that pressure means as pressure is increased, so the gas pores present in the liquid aluminum will agglomerate and condense into a big bubble. So that big bubble, as pressure is increased, that big bubble burst, and because of the bursting of that big bubble, that will impose some uh, like pressure, so that nuclei which are forming will disperse uniformly in the liquid aluminum and will result in the higher nucleation rate. Next is the electromagnetic convection. By electromagnetic convection, the solid nuclei which are formed previously will mix into the aluminum. So last method for the grain refinement is the severe plastic deformation. So in which different processes are used to uh, improve the heterogeneous nucleation sites available in the liquid solidified aluminum parts. So in the severe plastic deformation come into the category of dynamic recrystallization, DRX. So in this CDRX, this means continuous dynamic recrystallization, discontinuous dynamic recrystallization, and the geometric uh, dynamic recrystallization comes. Then next process is the this is up to the grain refinement methods, and so further the aluminum based metal matrix is studied. So what is the purpose of the this aluminum based metal matrix composites fabrication? because the composites have properties from the composites means the two or more materials are mixed together to achieve the combined properties. So the ductility of aluminum metal matrix with the high strength of reinforcement phase. So both means high ductility, high strength is achieved by forming these composites. And the aluminum alloys have generally the high ductility, that's why they are used with the high strength reinforcement phase. So the metal matrix composites have following properties, mean high specific strength, high modulus, low thermal expansion coefficient, high wear resistance, and corrosion resistance is also improved. So how we can make these metal matrix composites from the aluminum alloy and different reinforcement, whether it is fiber, uh, long fiber, short fiber, particulate, dispersed particulate, discontinuous reinforced metal matrix composites. So there are three state processing methods for for the fabrication of these aluminum-based metal matrix composites. So in the first method, which is liquid state processing method, first is the comes the stir casting. Second is the melt and filtration, and second is the spray deposition. So in stir casting, the reinforcement phase is faded into the liquid aluminum, and by the mixing and solidification that metal matrix composites is achieved. In melt infiltration, so in melt infiltration, uh, in this also the solid ceramic particles are fed into the liquid aluminum by some other method. And in spray deposition, the matrix droplets are sprayed from a chamber, and these droplets the spray of ceramic or reinforcement phase is done on these liquid droplets of aluminum, so that will attach with the aluminum and deposit on the surface. In the solid state process, powder metallurgy means we mix the reinforcement and aluminum powder together, then make some part, and then by sintering, we can achieve the final part from the of the composite. Then diffusion bonding means two layers of aluminum and composites, aluminum and reinforcement are arranged, and by diffusion at high temperature, these composites are formed. Then high energy, high rate means the aluminum foils, the aluminum foils and reinforcement are squeezed together at high energy, high rate, so that energy, high rate will ensure the complete compaction of these aluminum and fiber to each other, so to provide the uh, to create the bonds between the metal matrix and fibers, so that will make the composites. Then in the vapor state process, the chemical vapor deposition of both ceramic or metal matrix, so that chemical vapor is mixed to generate the uh, composite. Then physical vapor deposition, and further if the that metal matrix vapor is formed by the electron beam, then that is called as the electron beam PV, physical vapor deposition. During the vapor state process, means the solid reinforcement particle is added into the vapor of metal matrix and that is deposited onto a substrate. Then next is the reinforcement, how the it increases the properties of the metal matrix. So the reinforcement strengthens the metal matrix by grain refinement and increasing dislocation density in the matrix. So the wettability of the reinforcement phase is the crucial factor in providing the strengthening effect. Generally, the how we will define the wettability means if there is the contact angle between metal matrix and reinforcement is less than 90 degree, so it is a good wettability. And if we have contact angle between metal matrix and reinforcement greater than 90 degree, then it does not get by the metal matrix. So a low contact angle between the reinforcement and matrix lowers the energy barrier for nucleation and providing heterogeneous nucleation sites that results in a finer grain size. So one more factor in the strengthening is the uh, thermal conductivity ratio defined as alpha. So that is the ratio of thermal conductivity of reinforcement to thermal conductivity of the metal matrix. So if this ratio is greater than 1, that means the thermal conductivity of reinforcement is higher than the metal matrix. So the reinforcement particle will be engulfed in the metal matrix. And so means as the reinforcement particle is easily mixed into the metal matrix, so uh, that will be conducive, that will create the conducive environment for strengthening by providing the heterogeneous nucleation site. And if alpha it is less than, so if alpha is less than 1, then the solidification front of the metal matrix will push the reinforcement particle and will not add it in the uh, solidified metal. So that will not create any strengthening effect. Means the pushing of these particles will lead to clustering and segregation along the interdendritic region in aluminum alloy, so that will result in less strengthening. And if we consider if alpha is equals to 1, then planar surface between matrix and reinforcement and particle will form. Then next is the uh, role of mixture. So role of mixture we study to find the change in elastic modulus by mixing the reinforcement and metal matrix. So the elastic modulus changes with changing loading direction in composite corresponding to the reinforcement fibers. Means if we consider this is composite and fibers are aligned in this direction and we are pulling from this side. So in this condition, both fiber and matrix will stretch with the same amount. So in this strain will be, so this condition is called as the isostrain condition. So in this case, the strain of the composite will be equal to the strain in matrix and the strain into the fiber. And so that will lead to the elastic modulus of the composite as the EMVM mu m plus EF mu F. So here mu m and mu F are the volume fraction of metal matrix and fiber. So the volume fraction, if we talk, the addition of these two is equals to 1. So we can put the means Vm value from this equation. So this can be written as in the form of volume fraction of fiber also. So the in this isostrain condition, the modulus will be higher of the composite. And if we pull the material from this side, so in this condition, the strain in the matrix and fiber is not equal. Means is the here in this condition, EF is not equal to EM, and that will also not equal to EC. So, but the load will be same. Means PF will be equal to PM plus PF. So in this condition is called as the isostress condition. So isostress condition will decrease the elastic modulus. So in the isostress condition, we will achieve the less elastic modulus as compared to the isostrain condition. And the by doing some derivation, we can achieve the critical amount of volume fraction of the fiber, which results into the strengthening of the metal matrix. So this can be defined as the sigma mu minus sigma m dash divided by sigma fu minus sigma m dash. So here sigma mu is the UTS of metal matrix. Then sigma Fu is the UTS of reinforcement. Then and the sigma M dash is the flow stress of matrix during uh, deformation of during elastic or yeah elastic deformation of fiber. Means if we discuss this, means the stress strain diagram for the composite and matrix and fiber, if we draw, so for reinforcement, the this is the stress strain behavior for the uh, reinforcement, means very low ductility and high strength. For matrix, we will get the stress strain curve as this. So this is for the metal matrix. So means the low strength and high ductility. But if we talk about composite, so it will have the combined effect of the reinforcement and metal matrix. So this will achieve this, means high strength and high ductility. So if we deform the composite, so during that condition means the metal matrix is already deformed before the reinforcement particle break. So this is the flow stress when the reinforcement does not reach the fracture point of the reinforcement. So that is in that condition that so the sigma m dash is called as the flow stress of metal matrix during deformation of the reinforcement in the composite. So that's why the sigma m dash is coming in that equation. Then further, we can tell that there are different strengthening mechanism in composites also. which results in higher strength of the composite. So first is the shear lag theory. So lag theory tells us the transfer of load from metal from matrix to fiber. So how efficient the transfer of the load in matrix and fiber depends on the bonding of the this matrix and fiber. If bonding is good, then the transfer of load will be easy, and if bonding is not good, so that will result into the early failure of the composite. And next is the dislocation strengthening, means the a fiber present in the material will provide heterogeneous nucleation site in the metal matrix, so that will increase the dislocation density. Yes, so strengthening means the more dislocation will generate in the composite. And green boundary strengthening means the higher heterogeneous nucleation sites is available due to the fiber introduction, so that will improve the grain size. In work hardening, if we consider, work hardening is the deformation of a matrix is restricted by or got restricted by presence of reinforcement. So this restriction of the deformation of matrix will lead to constraint deformation. So this constraint deformation of matrix will result in work hardening of the composite. And due to the this constant deformation, the dislocation density will increase very significantly, so that will improve the strength of the composite. Then next is the coefficient of thermal expansion, means the thermal expansion coefficient. The thermal expansion coefficient is different for reinforcement and metal matrix. So because of the mismatch between the coefficient of thermal expansion, stresses will generate in the composite. So these stresses, the stress resulting from stress or stretching in the composite resulting from the mismatch of thermal expansion coefficient will further create dislocate forest dislocations. So now forest dislocations are generating from this coefficient of thermal expansion mismatch. So that will increase the dislocation density and increase the strength of the composite. So and next is the fatigue behavior of the composites, which we discussed in the last class. So we will not cover today. So that is all. So if you have any doubt, you can ask in the discussion forum also. So that's all for today. Uh, Thank you.